Chapter 7, Factorization. In this chapter, we're going to learn 5 new algorithms, 3 in unsupervised category and 2 in supervised category. So if I were to summarize this chapter, factorization, in one line, it comes back to this one line about data science. Data science is all about dimension reduction. Let that sink in for a while. Data science is about dimension reduction. By that, what do I mean by that, right? I mean, we get lots of data, we have lots of input, lots of variables, and we want to reduce that to low number of small summaries or small dimensions. And using those small dimensions, we want to make good decisions. So that's dimension reduction. That's also a technique of factorization. So given lots of input, lots of data, lots of variables that explain that data, how can we extract signal? How can we extract summaries that can represent the data so that we can make good decisions? That's the technique of factorization. So these summaries are factors. These are factors. So all related to what we're trying to do with data science, trying to make our machines be experts, right? And for that, they need to build expertise in, let's say, recommendation. Then they need few set of variables to do their job very quickly. So that's where dimension reduction and factorization comes in. So a practical example is Netflix, right? It has a recommendation engine which recommends us movies. How, for any new customer that joins Netflix, they're able to give them really good recommendations? Have you ever wondered how is it that they are able to get those people like the recommendations and actually watch the movies? So the way they do that is by using factorization techniques, and a specific one is the clustering technique that we'll go into. Basically, they cluster people like you because you give them some set of preferences, you give them some movies that you like, and you do actions on their platform which they learn from, and they cluster you with other people. They cluster you with other people. And they know that, hey, if Kunal likes these kind of things and then these other people all have very similar liking, then they put me in that cluster, and then I then follow the cluster, right? So that's the technique of factorization. It's how you cluster people as a specific example, right? We've seen that, right? It has, like, for a, let's say, a given person, they'll tell you like what are the top picks for you specifically, and then what's trending, right? And they show movies in from the most likelihood of being seen to the least likelihood of being seen, from the top to the right. So basically, this recommendation engine that they have built using factorization, using a clustering technique, which is a factorization algorithm, they are able to, at scale, give you recommendations. So what is this k-means clustering technique? So that's the first algorithm. So let's get into it. And for that, I'm going to open up Wikipedia, which does a pretty good job of explaining the basics of what k-means clustering is. In a sense, it aims to partition an observation into k clusters. Remember, I told you Netflix trying to put me into a cluster. So partition an observation, I'm an observation, into a cluster, people like Kunal, in which every observation belongs with the nearest mean. So meaning I have to be really belonging into that cluster, right? So that's that. That's it. That's it in summary, to simplify it. And there's a really good animation here. Take a look. It starts with all of these people here. And if you see the first iteration 0, which will start soon, you will see that it starts with pretty much random centers. Like this is a center, this is a center, this is a center. And then the center keeps changing as it tries to find out which person belongs to which cluster. And eventually it gets to an optimum, at which point it says, hey, this is the best setup. And there are only 2 steps, assignment steps and an update step. So for that, we'll get into what k-means does, right? So the way k-means works is tries to, in a sense, get you to be in certain cluster, like based on height and weight. In this example, it's trying to put people together in cluster. And so it has unlabeled data And using the k-means algorithm, you can actually create clusters of people. And so now all of a sudden you have shoppers, who have high price sensitivity in one cluster, shoppers who have low price sensitivity in one cluster, and Amazon can use that example and those clusters to say, hey, what should I recommend this person versus that person? Netflix can use this to recommend this movie to this person versus some other movie to some other person. So the thing to remember is that, as we saw in that animation, right, for every observation, there is a compute going on to find out which center is this point closest to. And then every time this cluster is getting updated, the new center is being generated. So it's very compute heavy. So that's the key thing to remember. It's very heavy on compute as the algorithm tries to figure out like what cluster you're part of. And K is, in a sense, it's like how many clusters, right? So K stands for, if it's 3 means, meaning there are 3 clusters. 5 means 5 clusters, something like that, right? And so grouping various people is a set of examples that I have given here, right? So I told you about how movies are being recommended. Similarly, music lovers, right? Pandora and others, YouTube, they figure out like what kind of music you really like, and then they recommend you those that autoplay after your chosen music is over. Or you can group voters as well based on like what drives their vote. So this is pretty important, pretty powerful to know how to cluster people, how to get them to be part of certain group where you can predict what they will do, right? So segmenting folks, segmenting customers based on their preferences, based on various algorithms is very powerful for you to predict and help your customers win. So here are the 4 steps. So the first step is you need to set the K. How many clusters do you want? And you start that, and clusters have cluster means, or like this centroid, or the cluster means, or the center, same thing, right? Once you set the number of clusters you want, you calculate the distance of each of these points to those centers. And you minimize that distance. Ideally, you minimize the sum of squared distance so that you don't have to deal with positives and negatives canceling each other out. And then you update the membership based on which point this point is closest to this cluster or this cluster or this cluster center. You just update that. And you can pick these random centers to start with, and then your centers adapt based on like who's closest to that center. So first step, set K. Second step, calculate for every point to every center that you have chosen at random, which center is the closest. And then once you assign and find out that center, you assign that point to that center so that membership is updated. And then you recalculate the center, because now all of a sudden you added a point into that cluster, requires you to recalculate the center. And so you need to iterate this until you minimize this overall distance for all of these points. And so then the question can come, how many, first of all, like I just assumed 4, should I have 4 clusters, 3 clusters, right? So there is a trade-off for every K. You will see that you increase the K, you can see a reduction in variance, overall variance, or the overall distances you can think about from each of these points to these centers. But at some point you will see marginal diminishing return, meaning you can't get more reduction in variance. At that point you stop. So you can draw an elbow plot. X-axis is K, number of clusters increasing. Y-axis is just the variance reduction that you get for every increase in the number of cluster size. And then you stop at a specific point. Remember, this is compute heavy. So you want to be very mindful on how and when, how much you run this algorithm. Then the last point on this is, if we started off with some random samples and random centers and random number of clusters, you will get some result. But if I instead of started with 2 clusters, I started with 3, I'll get a different result. Or if I started with some other data points, I might get as a starting point, then I might get different results. So then, is clustering really a good representation of the true state of the world? The answer is no. So we have to be very careful how we use this. At best, these are predictive summaries, or at best these are the likelihood scenarios, but that doesn't mean that these are representative of the true state of the world, right? So that's important to use this in business context that you're in. And it's an unsupervised learning because there's no why here that you're trying to optimize for. So that's K-means clustering, grouping folks together and using that power of that group to recommend, to predict, what kind of behavior this group is most likely to be driven by. Yeah. Next algorithm, principal component analysis, PCR. Same set of intuition even here. We're trying to reduce large number of input dimensions into a small number of output dimensions that you can use for prediction, right? Or finding out if we have several variables that impact, in this case, 5D plots, you're saying, hey, there are 5 variables. I want to find out the impact of each of these. So you reduce that down to 2 dimensions through a lot of math and figuring out how you take all of these input explanatory variables or X variables, which could have lots of collinearity, meaning they are correlated, right? So there could be that you're trying to predict, let's say, cholesterol based on age and food habits, right? Or blood pressure based on cholesterol and age, right? So there are 2 variables, but there could be so many variables that impact your cholesterol levels, but age and cholesterol levels all correlated. They go hand in hand in some sense. So how do you deal with correlated variables and still do your prediction? Right? So principal component analysis helps with that. So let's say we start with 2 variables, not even 5 as is shown here. We start with 2 variables and then we find out the center of those data points, right? You can find out the center of those data points by plotting those 2 variables on X and Y and then seeing what is the center of gravity or center that's most closest to all of these points, correct? You can find the center based on an X and Y plot. And then you move that center to be on the 0, 0, the origin. So move the whole plot to be on the origin. And then you fit a line. You're trying to reduce these 2 variables to one factor, one principal component. X1 and X2, you're trying to reduce that to PC1, principal component 1, right? So what you do is you first find the center, move the center to the origin, fit a line. How do you fit a line? We can do this with OLS, the ordinary least square technique that we've seen, or we can also do it using maximizing the projected distance of each of these points to that line. Same technique. You can say this in 2 different ways, right? Reducing the distance, the least square from that fitted line from each of these points is OLS, or maximizing the distance. In a sense, what you're trying to do is you're trying to reduce 2 variables to 1 variable. Let's say you had, you're trying to predict heart disease based on cholesterol and blood pressure. So you're trying to reduce blood pressure and cholesterol into 1 variable. So let's say X1 is blood pressure, X2 is cholesterol. You're trying to, that those are correlated because if you find the correlation between those 2, it'll be pretty high. And so we're trying to reduce that to PC1, one component that can be replacing both of those variables. So like you did this for 2 variables, you can do the same distance calculation and that fitting that line process for as many variables as you want. If you have a 3 variable X1, X2, X3, you have a line that's on a 3D space, right? But if you have 50 variables, you can have a line that's on a 50-dimensional space or a plane, and so you can do that for as many variables as you have. In a sense, you're trying to reduce input dimensions to smaller set of dimensions, especially those input dimensions. If they are correlated, you do that. Yeah. And so, like I've said here, you can do this for as many variables as you have. In a sense, you're trying to extract summaries. You're trying to reduce dimensions and trying to get the essence of what's in those variables by converting those multiple dimensions into certain components or principal components. That's this algorithm. And PC2 is an orthogonal line to PC1. So then you can quickly say, hey, if PC1 explains 80% of the variance and PC2 explains, let's say, 15%. So together it's like 95%, right? So you can say these components can reduce this large amount of input dimensions into a small amount of PC1 and PC2. So that's principal component analysis. That's, again, the intuition for how you can reduce and take out summaries, reduce dimensions, and extract dimensions from multitude of dimensions that you have. Now, building on, so that was PCR. This is PCA. This is wrong. This is PCA, right? And then we have PCR, principal component regression. This is principal component analysis. This is about finding out the principal components. PCR is basically, we have multiple linear regressions that we've seen in the past, right? If you have multiple variables, explanatory variables that try to predict y, you run a multiple linear regression, you get y as a prediction from each of those covariants or each of these explanatory variables. But what happens if these variables are correlated, right? Like blood pressure and cholesterol correlated, blood pressure, age correlated, right? So if you have those dimensions, then there's a problem. So what you do is you first run a PCA, find out and reduce those dimensions, take care of all of those collinearity, multicollinearity issues, because it's pretty dangerous, right? Because if you do an estimate, if you have input explanatory variables that are correlated, what will happen is your confidence interval will be pretty broad and your estimates wouldn't make sense. Some would be positive, some would be negative, even if each of those estimates are positively correlated. So your estimates, you can't make sense out of the multiple linear regressions. So you'd want to do a PCA first and then do a regression on top of those reduced set of variables. So that's PCR. You do principal component regression. So 2 steps: run PCA to reduce number of dimensions and use those low dimensions as covariance in your lasso regression, right? So now you have labels set, you can do that. So these principal components are independent, right? It removes this issue of correlated variables. And so you don't have to worry about multicollinearity, and it's easy to fit, right? And you can do this even when you have lots of unlabeled data, right? So because this is unsupervised learning, and you're trying to find out like what movie if this movie is the right movie to predict for this user, it's unlabeled. You don't know. You've not seen that movie before. It's a newly released movie. But you can use PCA to find out and predict and build clustering techniques to find out what will this person really like based on this unlabeled data, and still do your regression, right? So it has some parts of unsupervised learning, PCA here, and then it does a regression on top to predict the y, right? But remember here, it's still not trying to optimize for y. It's optimizing for reducing all of these x dimensions. So we covered supervised learning versus unsupervised learning in the past, but remember here, clustering is unsupervised learning, right? Where we have unlabeled data, new movies coming in, new songs coming in. We don't know for this person if this person would like this movie or not. There is no feedback mechanism. The k-means is what we've covered in this video. Last few chapters we've covered some of these. So this is unsupervised. And then the question is like, can we now combine the benefits that we get from unsupervised to supervised? That's where these two algorithms come in: marginal regressions and partial least squares. So think about this as partial least square is an iterated version of marginal regression, or a boosted version of marginal regression. We'll just cover partial least squares in this, which will cover some parts of marginal regression. So now what if we want to use all the benefits that we just learned about unsupervised learning with clustering and PCA into supervised learning, right? So that's where partial least square comes in. Partial least square is an iterated or a boosted marginal regression algorithm. And so we'll cover partial least square. By that, we will cover the intuition behind marginal least square as well, marginal regression. So partial least square uses the intuition of PCA, so principal component analysis, to extract and reduce components that optimize for predicting both explanatory variables, which is what we've done so far, and also the dependent variables. Look at that. That's the only difference. That's the only difference. So here we optimize for both X variables and Y variables. So we try to extract, like what we did for explanatory variables in the PCA, we do that also for dependent variables. So when you do both of those, X and Y variables, and you combine them to run a regression on that, that's partial least square algorithm at a high level. So it becomes a supervised machine learning technique, right? So again, it deals with all of those issues when you have input variables that are correlated or output variables that are correlated. And Nilesha did a pretty good job with this quality of apples prediction, right? So if you have a set of input features and output features, how do you make sure that all of those correlated variables like, manure and growth rate, manure and soil pH, and sugar content and weight, and there are certain Y variables that are also correlated, X variables are also correlated. So when you optimize for both, that's where you get partial least square. And so you can get the benefit of first running PCA, extracting all of the components like you did with previous one, the principal component regression. But here again, the difference is that you only do the fit for X, and then you do the Y prediction. Here you're optimizing for both X and Y. So that's partial least square algorithm. So the key things I want you to take out of this, folks, is about not the details of these algorithms, because you can get to a lot of these algorithms on your own, but to remember the fact that these are techniques to help reduce dimensions. And factorization is basically a way to get low dimensional or smaller number of dimensional summaries or factors that you can use to make predictions. And in this case, we saw how Netflix, Amazon, all of these big companies, social media companies, they use these algorithms to recommend, right? And recommend movies, recommend songs, and all of that based on your clustered membership, right? So that's the key takeaway as to how you do this clustering. So the one thing that I want you to take out of this is how you can use the power of clustering, power of factoring, power of factorization, where you can reduce from too many inputs to small number of dimensions and still make a good prediction, right? We talked about Netflix. Amazon uses the same. Pandora uses the same. YouTube uses the same. So this is a very powerful technique to create clusters. If you want to predict whether this price sensitivity of a person is low or high, and based on that, what their actions are based on a particular cluster, then you want to use clustering techniques. You want to reduce your dimensions to few actionable dimensions and make a decision. Yeah, thanks.